All right, so today we're going to turn our attention to focusing on hydrogen fuel cells. Specifically, I'm going to discuss in this lesson what a fuel cell is, highlight some of the main components of a fuel cell, describe the chemical process that takes place to show you that when fueled with pure hydrogen, the only byproducts given off by a fuel cell are heat and water, as well as provide you with a brief history of the fuel cell along with some of its various applications. As an introduction to fuel cells, take a few minutes to watch this video. So exactly what is a fuel cell? A fuel cell is a device that uses hydrogen or hydrogen-rich fuel along with oxygen to create electricity. Fuel cells are more energy efficient than combustion engines, and the hydrogen used to power them can come from a variety of sources. If pure hydrogen is used as a fuel cells emit only heat and water, eliminating any concerns about air pollutants or greenhouse gases. If you click the link at the top, it will lead you to a short video from Bill Nye discussing fuel cells. One of the most common types of fuel cells is the proton exchange membrane fuel cell, or simply known as the PEM fuel cell. The PEM fuel cell consists of an electrolyte membrane sandwiched between an anode, which is a negative electrode, and a cathode, which is a positive electrode. The PEM is a thin, solid organic compound. It typically has the consistency of plastic wrap and is about as thick as 2 to 7 sheets of paper. This membrane functions as an electrolyte, a substance that conducts charged ions, in this case protons, but does not conduct electrons. This allows the solution to conduct electricity. It's important to note that this membrane must be kept moist in order to conduct particles through it. As I just mentioned, when dealing with the PEM membrane, it's always sandwiched between both an anode and cathode, as you can see in the picture here. The anode is the electrode at which oxidation, which is the loss of electrons, takes place. In a fuel cell, the anode is electrically negative. The anode is composed of platinum particles uniformly supported on carbon particles. The platinum acts as a catalyst, increasing the rate of the oxidation process. The anode is porous so that the hydrogen can pass through it. In regards to the cathode is the electrode at which reduction, or gaining electrons, takes place in a fuel cell. The cathode is composed of platinum particles uniformly supported on carbon particles. The platinum acts as a catalyst, increasing the rate of the reduction process. The cathode is also porous so that oxygen can pass through it. So to describe the chemical process that takes place within any type of PEM fuel cell, to kind of get a better idea of what that looks like, hydrogen fuel is channeled to the anode, where the catalyst separates the hydrogen's negatively charged electrons from the positively charged protons. The membrane allows the positively charged protons to pass through to the cathode, but not the negatively charged electrons. The negatively charged electrons must flow around the membrane through an external circuit. This flow of electrons is what forms our electrical current. And as you can see here at the cathode, the negatively charged electrons and positively charged hydrogen ions, which are our protons, combine with oxygen to form water, H2O, and heat. So the amount of power produced by a fuel cell depends on several factors. These include the fuel cell type, the cell size, the temperature at which it operates, and the pressure at which the gases are supplied to the cell. A single fuel cell produces less than 1.16 volts, which is barely enough electricity for even the smallest applications. Because of this, to increase the amount of electricity generated, individual fuel cells are combined in series into a fuel cell stack. A typical fuel cell stack may consist of hundreds of fuel cells combined together. So for your convenience, I put this slide together to kind of summarize exactly how a fuel steps work with each of the processes involved. So that it's easier to understand exactly how a hydrogen fuel system works, for you visual learners, I provided you with this picture of exactly how the chemical process works. So as a reminder, a fuel cell is composed of 3 main components: an anode, a cathode, and an electrolyte membrane. The magic of the PEM fuel cell is in its proton exchange membrane, which again looks like a piece of construction paper. And it works by passing hydrogen through the anode side and oxygen through the cathode side. At the anode side, the hydrogen molecules are split into electrons and protons. The protons pass through the electrolyte membrane while the electrons are forced through a circuit, generating an electric current in excess heat. At the cathode side, the protons, electrons, and oxygen are combined together, and that's what produces water molecules. If you click the link at the top on how fuel cells work, you can click on this to see a quick short video describing this chemical process. So fuel cells are a flexible technology, and they have a broad range of applications for generating both stationary and portable power. Stationary fuel cell units can be used for backup power, power for remote locations, standalone power plants for towns and cities. It could be distributed generation for building, and cogeneration, in which excess thermal energy from electricity generation is used for heat. Fuels can also be used to power a variety of portable devices, from handheld electronics like cell phones and radios to larger equipment such as portable generators. They can be used for almost any application, typically powered by batteries, but they can last up to 3 times longer before refueling. Fuel cells can also be used to provide propulsion or auxiliary power for transportation applications, including cars, trucks, buses, trains, ships, and even submarines. They have also been used to provide auxiliary power on spacecrafts for decades. As you can see in the picture above, a fuel cell was modified by NASA back in the 1960s as a method to supply onboard drinking water as well as electricity for the astronauts aboard the Apollo space missions. An alkaline fuel cell is still used today in the present-day Space Shuttle orbiter. As I've mentioned in another video, states have introduced the Low Emission Vehicle Program, which offers large incentives for automakers to develop fuel cell automobiles. Automobiles powered by fuel cells are going to meet these requirements. The Netcar 5, shown here, is a prototype automobile by Chrysler. The automobile is fueled with liquid methanol and has a top speed of over 90 miles per hour. In the forthcoming years, there are plans for buses, trucks, and trains to all be powered with fuel cell engines. As we have seen, electrical energy demands throughout the world are continuing to increase, and there's many problems associated with the building of new power plants, both financial and environmental. Fuel cell distributed power stations can provide a solution through high-quality, reliable power. Shown here is a prototype fuel cell distributed power plant, recently developed by Ballard Power. It provides 250 kilowatts of electricity and about the same amount of heat fueled from natural gas. This is enough power to provide heat and electricity to a community of about 50 homes, for example, or to a hospital or even a remote location school. Fuel cell power plants are also being developed by several manufacturers to provide electricity and heat to a single-family home. Fueled by either natural gas or propane, these fuel cell power plants will be able to power a modern home. In order to harness more hydrogen, both scientists and engineers have been working together. One way to do this is to use reformers that convert a hydrogen-rich fuel such as natural gas, methanol, or even gasoline into pure hydrogen plus the emission of carbon dioxide. Hydrogen can also be produced sustainably from a system using a device that transfers the radiant energy of sunlight into electricity, such as a wind turbine, solar panel, or hydroelectric turbine for use by an electrolyzer. And then 3, there's also research and development taking place in the production of hydrogen from biological methods. For example, a green algae that electrolyzes water, producing hydrogen gas when sulfur is depleted from a water source. So why should we choose fuel cells? There's many different benefits. Fuel cells are more efficient. As fuel cells convert hydrogen and oxygen directly into electricity and water, there is no combustion in this process. As a result, the efficiency is high and about double that of an internal combustion engine. Fuel cells are also clean. If hydrogen is the fuel, there are no pollutant emissions from a fuel cell, only the production of pure water. In contrast to an internal combustion engine, a fuel cell produces no emissions. Fuel cells are also quiet. A fuel cell itself has no moving parts. As a result, a fuel cell produces electrical power virtually silently. Many hotels and resorts in quiet locations, for example, would like to replace diesel engine generators with fuel cells for both main power supply or backup power in the event of power outages. Fuel cells are also modular. That is, that fuel cells can stack together of varying sizes and they can be theoretically combined together to meet a required power demand. Fuel cells are also environmentally safe. They produce no hazardous waste products, only the production of water. And finally, fuel cells provide the opportunity to produce a sustainable source of electrical power. If fuel cells get their hydrogen from renewable energy sources, such as solar, wind, hydro, or biological methods, they can provide a sustainable source of electrical power. And you can see here, just by looking at this picture, there's been trends in the use of fuel over the years. As fuel has developed over time, the percentage of hydrogen content in those fuels has also increased. It seems as a natural progression that the fuel of the future will be hydrogen. The two principal reactions in the burning of hydrocarbon fuel are the formation of water and the formation of carbon dioxide. As hydrogen content in the fuel increases, the formation of water becomes more significant, resulting in proportionally lower emissions of CO2. A varied range of organizations, from energy companies to automobile manufacturers, are working to develop fuel cells and the accompanying infrastructure. A trend in the production of power is clearly visible here. In the 19th century, there was the steam engine. In the 20th century, that was the century of the internal combustion engine. And now into the 21st century, this will be the century of the fuel cell. And finally, I just wanted to provide you with a quick history on fuel cells. So the first fuel cell was developed all the way back in 1839 by Sir William Grove, a British scientist and lawyer. The principle was actually discovered by accident. He was performing an electrolysis experiment when he disconnected the battery from the electrolyzer and ended up connecting the two electrodes together. He noticed that a current flowed in the opposite direction, consuming the gases of hydrogen and oxygen. He called this device a gas battery. His gas battery consisted of platinum electrodes placed in test tubes of hydrogen and oxygen. Immersed in a bath of dilute sulfuric acid, it generated a voltage of about 1 volt. However, Grove's fuel cell was not practical due to problems of corrosion and instability of the materials. As a result, there was little research and development into fuel cells for many years to follow. But finally, significant development on the work of fuel cells began in the 1930s by Francis Bacon, a chemical engineer at Cambridge University. In the 1950s, Bacon successfully produced the first practical fuel cell, an alkaline fuel cell. It used an alkaline electrolyte instead of a dilute sulfuric acid. The electrodes were constructed of porous sintered nickel powder so that the gases could diffuse through the electrodes to be in contact with the aqueous electrolyte on the other side. This greatly increased the contact area between the electrodes, the gases, and the electrolyte, thus increasing the power density of the fuel cell. In addition, the use of nickel was much less expensive than that of platinum. An assistant can be seen in this photograph mounting a plate onto the side of Bacon's fuel cell stack.